Good morning, students. Today, this is our fifth lesson on electromagnetic induction and alternating current. And today we will be discussing AC generator. What is AC? It's not air cooler.
Alternating current.
Yeah, it is alternating current or changing current. And we can't call all changing currents AC. So we will see first what is alternating current. How is it different from DC and other currents? Then we will see how it can be generated using a AC generator, which we also call a dynamo. And then we will see different parts of the dynamo and how it works. Here you can see this picture. This is an animated picture of a AC generator. So let us see what is alternating current. Here you can see a circuit, a simple circuit where a battery is connected to a resistance. Here we have a positive terminal and a negative terminal, and therefore we know that current will be flowing from the positive terminal to the negative terminal through this resistance. So the current will flow in one single direction. Such currents are called direct current, and they will have the same magnitude. Here in this graph, which is drawn with time taken along the x-axis and current or voltage along the y-axis, this red line represents direct current. See, it's going in the same direction. It's not becoming positive and negative. It's in the same direction and its magnitude is not changing. Such currents are called direct currents. Now, in alternating currents, we cannot show the terminals as positive and negative. This is the symbol for alternating current. See, it's like a sine wave. It's like a wave. So it is changing. And you cannot determine a fixed direction for current as well. See, it's shown in either directions here. It can go in this direction or in the other direction. So it keeps changing. And let us see this graph. Here you can see a blue line. This current's value is also changing, right? But it is not AC. It is pulsating DC or pulsating direct current. See, it is going as pulses, but it is never becoming zero. It's not going to the negative of the axis. So it's just pulsating DC. And here you can see a gray line that is showing another variable current. Its value is changing. See, sometimes it is negative, sometimes it is positive. Its value is changing. Still, it is not alternating current. It's variable current. Its value is changing. Now let us see what is an alternating current. An alternating current or AC is an electric current which periodically reverses direction. See, periodically reverses direction means reverses direction in a fixed interval of time or in a fixed period and changes its magnitude continuously with time. Now see the green line. Here you can see that the green line is changing continuously and it is changing direction after a fixed interval of time. So if this total time is say 2 seconds, then after 1 second it changes its direction. In the first second it was positive, in the second second it is negative. So this is called an alternating current. The green line represents alternating current. So every changing current cannot be called alternating current. Is that clear to you? What is alternating current? Is that clear to
Yes,
you?
teacher.
Yeah.
Yes, teacher, clear.
So alternating current is an electric current which periodically reverses direction and changes its magnitude continuously with time. And what is electromotive force? Nothing but voltage. So what is alternative voltage or alternative electromotive force? It is the electromotive force due to which an alternating current flows in a circuit. So the AC current is caused due to a alternating voltage or alternating EMF. That is called alternating EMF or electromotive force. Here you can see different alternating voltages or alternating EMF. One of it have a maximum value 120 volts. So here, see, it varies from 0 voltage, goes up to a maximum of 120 volts, and then it goes to 0 again, reverses its direction, again goes to value minus 120 volt, and then goes to 0. Like that, it continues. So this is another AC voltage or alternating EMF, and it has a continuously changing magnitude and it reverses its direction periodically. And another one having a higher voltage. See, it goes from 0 to a maximum value of 240 volts, and then it becomes 0 again, reverses its direction, has minus 240 volt in the other direction, and again becomes 0. So this is alternating voltage. So alternating voltage and current both vary in fixed interval of time. So let us see now how we can produce this alternating current using a generator or dynamo. Have you learned about AC generators and dynamos before? Have you learned it?
No.
No, you are learning it for the first time. Okay. So what is a AC generator or a dynamo? It's a device that converts mechanical energy to electrical energy. And it works on the principle of electromagnetic induction. Who put forward the rules for electromagnetic induction?
Faraday.
Michael Faraday. And he proposed two laws, right? The first law states that a EMF is produced whenever there is a change in the magnetic flux linked with the coil. So we learned this equation. EMF is equal to minus N times d phi by dt, where EMF induced is epsilon, N is the number of turns in the coil, phi is the magnetic flux, and d phi by dt is its rate of change with time. And the negative sign was given by Lenz's law. That is, the EMF will be opposite to the cause, that is, the change in magnetic flux. Now we also learned that the magnetic flux is equal to BA cos theta. Can you tell me what is B?
Magnetic field.
A,
Area.
area of cross section, or it is a vector, area vector, which is always perpendicular to the surface area. And what is theta?
Angle between the magnetic field and the area vector.
Area. So we can change magnetic flux either by changing B, the magnetic field, the area A, or the angle between them. So in an AC generator, we are producing EMF by changing theta, the angle between magnetic field and area. How can we change theta? By rotating. Okay. So in an AC generator, theta, the angle between magnetic field and area vector, will be changing. That is by rotating. So let us see how it is done. Here you can see a diagram showing different parts of an AC generator. An AC generator consists of two poles, north and south of a magnet. Here you can see a magnet shown in blue color. There is a north pole and a south pole, and there is a coil of rectangular shaped wire known as armature. Armature means this coil of wire which is rotating. So the rotating part of a AC generator is called armature. So this coil is called the armature because it rotates. And the armature is connected to two slip rings. Here you can see two rings. These are metallic rings which are connected to two ends of this rectangular coil. See, one end is connected to one ring and the other end is connected to another ring. This end is not connected to the first ring, okay? So only one end is connected to one ring and the another end is connected to the second ring. So these are called slip rings. Why they are called slip rings? Because they slip across two carbon brushes. So this carbon is a conductor of electricity. So metals are conductors of electricity. So whatever current is produced in this rectangular coil will flow through the slip rings, then it will pass through the carbon brushes and get into the external circuit. So the slip rings provide a continuous connection with the wire around the armature. The slip rings are attached to carbon brushes, as you can see here. And the rectangular coil is capable of rotating. It can rotate easily about an axis, which is perpendicular to the magnetic field. You know the magnetic field will be from North Pole to South Pole. So it will be in this direction and the axle is perpendicular to the magnetic field. And this rectangular coil of wire, suppose this is the rectangular coil of wire, it is rotating in between. It is free to rotate. So these are the parts of a AC generator. What are the parts? It has a magnet, a armature, two slip rings, carbon brusher, and this armature rotates about an axis which is called an axle. Is this clear to you, the parts of a AC generator?
If we
Yes.
changes the position of the magnet, then it will change. I mean, it will rotate in
Yes. Yes.
another direction, right?
If we change the position of the magnet or the value of the magnet, strength of the magnet, then also it will the flux will change. But usually the magnet will be very heavy and it's not very easy to change it. But this coil of wire will be lighter and it is easily rotatable. So we will rotate that. There are different types of power station. For example, you must have learned hydroelectric power stations where water falls from a height. And when the water falls from a height, it is rotating the turbine. The turbine is connected to this rectangular coil or armature. So the turbine will rotate, and what happens? The mechanical energy of water gets converted to electrical energy in the coil. Another engine's steam engine. In steam engine, the steam is pushed at high pressure. So when the steam pushes, this coil rotates. Again, the energy from the steam is converted to electrical energy. Also in nuclear power stations, due to nuclear reaction, some heat is produced that is used to boil water, and the steam is again pushed at high pressure and this will rotate the coil. So in every power generator, the basic unit that converts mechanical energy to electrical energy is this AC generator. So whatever power station it is, there will be this AC generator. Yes, is there any doubt here? In the parts of a AC generator, we will see how it works.
No, teacher, no doubt.
Okay, so let us see how a AC generator works. So you must be knowing these two equations. Now let us see the working of an AC generator. So you remember the equation, right? Phi is equal to BA cos theta. Now, initially, when the time is 0, theta is 0, which means the magnetic field and area vector are in the same direction. See, look at this figure. Stage 1. The plane of the armature is perpendicular to the magnetic field, which means the magnetic field is like this. Suppose here you have the North Pole and here you have the South Pole. So the magnetic field is coming in this direction. The area vector is also in the same direction. So initially, that is when time is equal to 0, theta is equal to 0. And theta is the angle between the magnetic field and the area vector. So magnetic flux phi is equal to BA because cos 0 is 1. So initially magnetic flux phi is equal to BA. Now when the coil rotates with an angular velocity omega, have you heard of angular velocity?
Yes.
Yeah, any rotating thing will have an angular velocity. And what is theta? If omega is angular velocity, what is theta? Theta is
Angle difference.
angular displacement. Okay. So when a body rotates, what is changing? Its angle is changing. So we call theta the angular displacement. If a body is having translational motion, its position changes, right? And the change in position is called displacement. That is called linear displacement. Now, similarly, when a body is rotating, its angle is changing. So we call that angular displacement. Theta is angular displacement and omega is angular velocity. So theta is equal to displacement is equal to velocity into time. So you can tell angular displacement theta is equal to angular velocity omega times time. So when the coil rotates, after some time, the coil is rotating, right? So after some time, if theta is the angle between the area vector and the magnetic field, then theta will be equal to omega t. So in magnetic flux, BA cos theta, instead of theta, we are substituting omega t. So we get it as BA omega t. So at any time, we can say that the magnetic flux is equal to BA cos omega t. Is this clear to you? How I wrote instead of theta omega t? Say yes or no. Is it clear why
Yes, teacher.
theta is omega t? Yeah. So it's the angular displacement theta. Now, by Faraday's law, you know that the induced EMF is equal to minus n d phi by dt, right? So instead of phi, let us put BA cos omega t. So EMF is equal to minus n d by dt of BA cos omega t. Now we have to differentiate BA cos omega t. B and A are not changing. We are not changing the big magnet over there. And we are not changing the area of that rectangular coil. They are part of the machinery. So they will be remaining constants. So we can take both the magnetic field B and area vector out of the derivation. So it will be minus n BA d by dt of cos omega t. What is d by dt of cos theta?
Minus sin theta.
Minus sine theta. But here I have written omega sine theta. Minus gets cancelled because of the minus sign. Can you tell me why it is omega sine omega t? You have to differentiate theta also with respect to time. Can you see the whiteboard here behind me? If I write something on the whiteboard, will it be observable for you?
Yeah, we can see this.
You can see the whiteboard here, right? So we have here, I'll just write, we have here phi is equal to BA cos omega t, right? That is BA cos theta. Instead of theta, I wrote omega t. Is this clear to you, or I should stop sharing?
Yes, clear.
Clear to you? So cos theta. Now, when I am finding EMF, EMF is equal to minus n d phi by dt, right? So instead of phi, I'm substituting BA cos theta. So this is equal to minus n d by dt of BA cos theta. Now B and A are constants. I'm taking out. This is equal to minus n BA d by dt of cos theta. Is this clear? Till this it is clear?
Yes, teacher, clear.
Okay. Now theta is a function of t, right? So I can write this as equal to minus NBA d by d theta of cos theta, cos d theta by dt. Can I write like this? NBA,
Yeah, got it. Chain rule. Yeah.
chain rule we have to use here. So this is equal to minus NBA d by d theta of cos theta is minus sine theta. Okay, minus sine.
Teacher, can you explain that line?
1 minute. I will stop sharing so that you can see the whiteboard large. Can you see now?
That last line. Can you explain the last line?
This one?
Yeah.
Yeah. Let me tell you. Suppose you have a function u of t. U is a function of t. Suppose. Okay. Then du by dt. You want to find. Okay. Suppose you have u, which is a function of v. So, and v is a function of t. Then you have the chain rule. If you want to find du by dt, you have to do what? Du by dv you have to do, then dv by dt. See, they gets cancelled. Have you learned this in math before? This is called chain rule.
Yes, teacher, we learned.
Okay. Here we have d by dt of cos theta. There is no t here. But we know that theta depends upon t. Theta is equal to omega t. So,
I understood. Now I understand. We have
so
to differentiate theta also, right?
yeah, so you have to differentiate theta with respect to t.
Okay, teacher.
Now is it clear?
Yes.
Okay. So what I did was I wrote first d by d theta of cos theta minus sine theta, and d theta by dt. What is theta? Omega t. D by dt of omega t is omega. So I got here omega. Now what I did was minus times minus plus. So NBA, sin omega is there. So that omega and sine, instead of theta, we have wrote omega t. Is this clear? How we got this expression?
Yes,
EMF
teacher, clear.
produced is equal to NBA omega sine omega t. And this is the EMF produced, right? N is a constant. Number of turns of the coil is a constant. B is another constant. A is constant. And if we are rotating with a fixed angular velocity, omega also will be constant. So all these constants we can say together as epsilon naught into sine omega t. Okay, so what is epsilon naught? It is equal to NBA omega. Okay, all these are constant. Number of turns are not changing. B is not changing. A is not changing. Omega may change. Okay, omega may change, but if it is constant, this will be constant. Now, what is the value of sine omega t? How will sine change? What is the maximum value of sine theta?
1.
1. What is the minimum value of sine theta?
-1.
-1. Right? So, value of sine theta changes from -1 to +1. Okay? So, the value of epsilon E will become equal to maximum value of E possible will be plus E naught. And the minimum value of E possible will be equal to, when E sine is -1, minus E naught. So the EMF will vary from plus E naught to minus E naught. It can become 0, plus E naught, 0, minus E naught. So let me again share the screen with you. Okay, let us again share the see here. Okay. Here we saw that EMF E is equal to E naught sine omega t. What is E naught? NBA omega sine omega t, which we have derived here. Okay. So as sine omega t is a periodic function and it varies from -1 to +1. So the minimum value of E possible is minus NBA omega when sine omega t is -1. And the maximum value of E will be plus NBA omega when the value of sine omega t will be +1. So the EMF varies between these two values. And this value is called the peak value, epsilon naught. It has a value NBA omega. Okay. Now, this is the voltage. How can we find current if we know the voltage? By Ohm's law.
I equal to V by R.
I is equal to V by R. So you can say if this is the induced EMF, the induced current I will be equal to induced EMF divided by R. Okay, so EMF divided by R sine omega t. E is equal to E naught sine omega t. So I will be equal to E naught by R sine omega t. And we can call E naught by R as I naught. And this E naught, that is the maximum and minimum value of EMF, is called the peak values. So it goes up to a maximum of E naught and comes to a minimum of minus E naught. So these two values are called the peak values of EMF or peak values of voltage. Similarly, you can get the peak value of current by peak value of EMF divided by R resistance. Okay, so you just have to learn this formula. E is equal to E naught sine omega t, where E naught is equal to NBA omega. And just remember that I is equal to E by R. And I naught will be equal to E naught by R. Just divide that value with resistance, you will get the current. Okay, now let us see how this value changes as the coil rotates. Suppose initially we said that here the area vector is in the direction of the magnetic field. So here magnetic field is in this direction, area is in this direction. What is the angle between them? 0. So what will be the EMF? Angle between them is 0. What is sine 0?
0.
0. So the EMF is equal to 0. So initially when we start from this position, EMF, induced EMF will be 0. Now suppose this coil is rotating through an angle 90 degree. See, it has rotated through an angle 90 degree. Now you can see that the area vector is in this direction while magnetic field is remaining in the same direction, north to south. So what is the angle between the area vector and the magnetic field now?
90.
90 degree. What is sine 90?
1.
1. So what will be the EMF? EMF will be equal to E naught, that is NBA omega, or the maximum value. Here you can see in the graph, it goes to the maximum value once it rotates through 90 degree. Okay. Now again it rotates through 90 degree. Now what is the angle between the area vector and the magnetic field? Magnetic field remains from north to south while the area vector have rotated through 180. So what is the angle now? 180 degree.
1.
So what is sine 180? 0. So the induced EMF also will become 0. Can you see here in the graph? So when we rotate through 180 degree, at 90 it becomes maximum. 180 degree rotation, it will again become 0. Now again we are rotating through from 180 to 270 degree. 270 degree, if we are rotating, what happens when it becomes 270 degree? Then what is sine 270?
1.
Minus 1. Sine 270 is minus 1. All silver teacups. Have you learned about that? All silver teacups. All silver teacups. So
Yes.
0 to 90 degree, all functions will be positive. 90 to 180, only sign will be positive. 180 to 270, sign will be negative. Only tan will be positive. Is that clear? So it will be minus 1. Sine value will be minus 1. Sine 270 degrees minus 1. So what happens? It goes to minimum. Minus E naught. What is that? Minus NBA omega. So the negative peak value it becomes. Again, when you rotate through 360 degree, see it came back to the original position here. See, so it came back to the original position. So again becomes 0 and it repeats for each complete rotation. What happens, the EMF will vary from 0 to a maximum value, then 0, then minimum value, and then again 0. Is this clear to you?
Yes, teacher.
Okay. If you call the total time taken for this one complete rotation as capital T, the period, then in quarter of the time, it goes from 0 to maximum value. That is T by 4 time. Now, again what happens? Again, if we continue the rotation in half of that time interval, it goes to the maximum and come back to 0. That is T by 2 time interval. Again, when you rotate in 3T by 4, what happens? It will become negative. And the next quarter, it will again go to 0. So this is how it changes like a wave. Is it clear to you, the working of a generator?
Yes, teacher.
Okay. So today we have learned what is alternating current, what are the parts of an AC generator, and how it works. So in next lesson, we will learn more about alternating current, a few more terms related to alternating current. So is this clear? Is this topic clear to you?
Yes, teacher.
Okay.
Teacher, the time will finish now.
Yes.